your big signal at the highest level of we have tech debt or too much tech debt in data engineering. We have pipelines breaking. We have cloud bills. Then we have large cloud bills that are maybe out of control cloud bills. We also have multiple sources of truth. It's another interesting tech debt problem. And then you have unclear data sets that aren't documented. So each one of these has their own kind of like remedies to kind of fix. We're going to go over kind of some interesting remedies that we can go over for each one of these buckets so that we can know how to maybe fix some of this stuff. Okay. Say you have a painful pipeline. You have a pipeline that's breaking, and say it's every on call. So you have an on call, and then it's like every Saturday and Sunday it breaks, and it ruins the on call's weekend. And then it's like, then you just dread being on call because you're like, I have to give up my weekend, and I don't want to do that because like a lot of times, like if you're on call and it's the weekend, and then you have to work on the weekend, and then you get no break, and then you have to go immediately into work after working on the weekend, you're like, data engineering is freaking me out right now, man. I don't want to do it. And so that's where troubleshooting these problematic children and these problem pipelines can be very important. So the only thing, I like this. The only thing better than optimized is deprecated. I love that saying because it's like, that's how you get the most efficiency, right? Is like, if you just delete the pipeline, you save the most in the cloud, right? If the pipeline doesn't exist. Obviously, that's not always the case of what you want, but so sometimes deprecated is the right play. I want to talk real quick about an example that I had at Netflix that was interesting. So when I was working at Netflix, I worked in detection, right? And so in detection, they had this like legacy system for detection that was based on, it was a batch processing legacy system. It was like an hourly batch processing legacy system. And it ran in, I mean, it was like a suite of like 50 pipelines that were all running to like detect anomalies in the cloud environment. And the security team was like, this isn't good because it detects anomalies an hour late. And we were like, yeah, that kind of makes sense. That makes sense why that's not good. And then like we were like, okay, we're gonna move some of them to streaming. We're gonna move whatever we can to streaming. And but then we realized that like even before we moved everything over to streaming, we recognized that they weren't even using the data anyways. So we were like, why are we paying this maintenance cost every single day on these like 50 plus pipelines for data that's not even being used, data that's not providing any value? Like, why are we even doing that? So uh Like, so what we did was we got everyone into a room and we were like, can we get rid of this? Do we even need this? Like, this is causing us a lot of headache. Do we even need to have these pipelines around anymore? And there was a lot of pushback because there was essentially the like, what if we need to run a query? And then we talked with them and we're like, you haven't ran a query in the last 60 days. So that what if is like, maybe that's not like actually going to happen. But obviously security is an interesting space, right? Because it's like you want that you only need the data when like something bad happens, right? So it's like a lot of the times like maybe you don't need the data, but it's kind of the idea here. That was something that we ended up doing there. We actually were able to convince them. It took like, it was like a 6-month process of convincing them to delete these pipelines, but we were able to do it. And that made our lives a lot better because then our the maintenance burden for the on-call dropped like, it went from like on-call being terrible to on-call like almost being nothing. And so a lot of times that can be the case. And there was like, because the thing was those pipelines were already as optimized as they could be. There was nothing else we could do to make those pipelines better. It was just that there was a lot of them and that like they were doing a lot of work. And that like once like you kind of have the tragedy of commons, you have the like Murphy's Law or something like that, like where once you have enough of something, you're guaranteed to have one bad of that, right? It's like once you have a room of enough people, right, you're guaranteed to have at least one asshole, like just guaranteed, right? Because like that's just how people work. Or there's a certain percentage, even if it's like 1% or 0.5%. Like once you have enough people, you're guaranteed that there's going to be at least one asshole in that room. And so same perspective here, right? Where it's like, okay, well, like maybe we shouldn't try to spend all of our time and effort optimizing these pipelines, but we should actually just delete them. And in that case, it was actually the right call. And so like that's one of the things that you got to remember about, especially when you inherit pipelines, and they weren't necessarily pipelines that you built yourself, but you inherit a suite of pipelines from another team or another engineer. Like question the value and actually ask yourself, like, is this worth being on the on-call rotation? Is this something that should actually be troubleshooted over the weekend? Because maybe it's not, and maybe it shouldn't even exist. And if that's the case, then deleting it is great because then your on-call becomes way easier. And like I'm sure some of y'all like are like, Zach, that sounds like kind of like too good to be true, or like, because I think all of us have had nightmares as data engineers where we were like, you know, our life would be a lot easier if we just deleted all the pipelines, and then there would be no data, and then our lives would be solved, and then we wouldn't have to do anything, and then all the buzzing in our head and all the anxiety in our hearts would go away. And but like in some cases, I've actually had a couple cases in my career where that was the call. So is there anything that can be done with this, right? Besides deleting it, you can migrate to new technologies. It's great. You can maybe implement better data modeling, so you have fewer pipelines that are running because you have more robust data modeling where like you don't have to have like duplicative models, and you kind of have like one model or one pipeline that produces a more robust model. Because then it's like if you can say you have a suite of 100 pipelines and there's a 1% chance that things break, then that means that something's going to break every day. But if you have 10 pipelines and there's a 1% chance that things are going to break, that means that things are going to break like a couple times a month. And big difference. Very big difference. Like especially if you can keep the failure rate the same and you can make the modeling better, then like the consistency at which your things actually fail, because things are going to fail. Pipelines fail. Like and like nothing's perfect, and don't ever expect to write a pipeline that's never going to fail. Like it's going to fail, and it's just all about like the frequency and the rate and all that stuff that you want to think about, right? Other things that you might want to consider when you have a painful pipeline is can you bucket the table? That can sometimes help quite a bit. I'll talk more about some examples that I've had in my career where bucketing was like a silver bullet. And the other one is sampling. Sampling's great. A lot of times you just need directionality. You don't need every single record. And if you can just like get a 1% sample, then you just get a 100x reduction in the complexity of that pipeline with like one line of code. And sometimes that's the solution. Just don't process all the data. Like I know these solutions seem like in some ways they're not like tackling the scale. They don't sound sophisticated, but they're smart. That's the part of it that's great, is that like if you have a bunch of pipelines that are processing a lot of data and they're not providing that much value and they're causing you a lot of headache, like this is a beautiful path forward that can actually work, and especially in terms of maintenance. And I've seen this work many times, and definitely remember that deleting the pipeline could potentially be a tool in your tool belt. You don't have to just optimize it. So that's a beautiful path forward. I love it. So I'm sure some of y'all have upgraded from Hive to Spark. It's probably a common thing that y'all have done. I've seen massive gains here, but there's also like it's interesting because this promise is not linear or not uniform, right? Because a lot of times like some people are like, oh, if you migrate from Hive to Spark and you'll see a massive performance gain, and that's only in the case of very specific types of pipelines, and they have to like essentially use like a very high cardinality group by or high cardinality join they have one of those two keywords in your SQL, then migrating from Hive to Spark, you're going to see a massive gain, like probably between 50 to 90% more efficient. And like it's awesome. I think one of the things here that some data engineers make a mistake about is they promise more because they think that that's going to be the case for every pipeline. But some pipelines you're going to see flat. Some pipelines are going to be only 5 or 10% more efficient, but there are some edges where like it's really a lot more efficient. Where because Spark versus Hive are very interesting because Hive does everything like on disk. It doesn't use RAM at all. Like blows my mind that that's what we did for so many years. It's like we're just going to write all our data to disk forever. But in the same vein though, because Hive does everything on disk, it's very resilient. And like a lot like Hive might be really slow because it does everything on disk, but it's definitely going to finish. Whereas Spark might actually fail. Like that's one of the other things I noticed when I did some Hive to Spark migrations is Spark was more efficient but less reliable. Where like Spark is actually more prone to out of memory exceptions and more prone to skew than Hive is. So when you do these migrations, sometimes like it's a trade-off. It's not just like you're getting it's not like an upgrade. It's like you're getting a certain set of traits, but you're losing other set of traits. And for the most part, the trade-off is worth it, and that's why people do the migration. But that's what I'm saying is that like Hive pipelines are technically more reliable. They're more reliable but less efficient. So that's the thing to remember. And the main reason for that is because they do all the calculations on disk, whereas Spark uses RAM. And that can be one great way to improve the kind of efficiency of your pipeline and the landing time and all sorts of other things like that. But not necessarily the reliability, right? Because the reliability is the one side that like Hive and Spark are like Hive is actually has a slight edge. So that's one thing you can do. Upgrade the technology. Another option here, right, is maybe you want to move to like streaming, or you want to move the pipeline to streaming. Obviously, that should be something that should be taken very like you should be thinking through that problem a lot. Like definitely like don't just bring in Flink. Like you should only be bringing in Flink after like you've really thought about it, and that's really the only thing that you should do. Right? It's not necessarily like an upgrade problem. That's more of like I need to solve a new use case problem. But in some cases, streaming can actually be more reliable because of the fact that it's just processing data as it comes in, as opposed to processing some big batch of data. And then that can make it so that the memory footprint of the job can actually be more consistent, and you don't have these big spikes in the memory footprint. And because when you have a job that has big spikes in the memory footprint, that's when you have jobs that are more likely to run out of memory. And especially like in Spark, right, there was that hard limit, right? You have that 16 gigabytes, right, where it's like if you have a partition that ends up being bigger than 16 gigabytes for whatever reason, because of skew or whatever other reason, then it's going to be more unreliable than a streaming job that potentially won't have that same spike because of the fact that it processes the data as it comes in. So that can be another potential thing that could increase the reliability of your pipelines. So technology upgrades, pretty cool. So sampling, I love sampling. I want to talk a little bit about an example, kind of war story from my time at Netflix. So one of the things I worked on at Netflix was how to create a metric that measured the amount of incremental AWS cost from an A/B test. So it's like, say you have two like a test and control group in an A/B test, and one of them causes the app to make more requests to the server, and then that server will send more data down. But maybe like it's 10% more requests, so then the server load is 10% more or something like that. And so like the way that I was looking at that originally was like, okay, I'm just gonna look at all the network requests that that Netflix receives, and it's like that's a very big data set. That data set is hundreds of terabytes an hour. And the metric that we were like, and if you're processing hundreds of terabytes an hour, that's millions and millions of dollars a year in cost, like in actual cost to the company. So, and our metric that we were making was probably not going to save that much money. So like we realized that like, okay, like there's an ROI here where it's like we need a sample, we need to like cut the data down, and maybe only we ended up using like less than 1%. And since we were able to cut down the volume, and because we only need the directionality of the sampling or of the data, not the whole like data set for auditing. And so that's a good way to do it. Before you set up sampling though, make sure that you don't just like just set up whatever sample thing you want to do. This is something where like you do want to consult a data scientist about the data shape, so that like, because it's very important to get a random sample. But for example, here is another thing to think about with like requests. I think this is a beautiful example where like I think as data engineers this isn't something that we think about that much. But like, okay, there's two ways that you could sample the requests, right? Where it's like you could take a small percentage of all the requests and just randomly take a percentage of all the requests, or you can take all the requests for a small percentage of users. And then you get the whole flow for every user, but you only take a small number of users. Or do you just take a small number of all the requests across the board? And those are, you could get the same percent, you could get the same like reduction, but it's all about like what rows you pick and what rows you filter out. And that makes a very big difference on the data set itself and like what you're trying to solve for. Like, for example, in this case, the better solution here was to pick users and get the full request history for individual users, not filter to like random requests across the board, because then you get the full kind of makeup of like the whole like request flow for each user, and that's a better aggregation model than like in this other case where it's like you have like one request for this user, two requests for this user, and it's like kind of like you don't have their full history. So like the analytical capabilities of that way of sampling versus the other way of sampling is significantly different. So that's where like don't just like be like because it's easy to sample, very very easy to sample. Like it's a one-liner to put that into sampling, but don't do that. Like make sure to ask a data scientist. Like that's my main point there. Unless you are amazing at statistics and you already have the data science skills, then maybe do it yourself. But I know I don't. That's one of the things that I recognize that I want to defer to a data scientist about, because that will make the whole process a lot better. So remember, sampling is another beautiful tool in your tool belt if your pipelines become more unreliable and you don't need the full data set. Tool, like because it's easy to sample, very very easy that Netflix receives, and it's like that's a very big data set. That data set is hundreds of terabytes an hour, and the metric that we were like and if you're processing hundreds of terabytes an hour, that's millions and millions of dollars a year in cost, like in actual cost to the company. So, and our metric that we were making was probably not going to save that much money. So like we realized that like okay, like there's an ROI here where it's like we need a sample, we need to like cut the data down, and maybe only we ended up using like I think less than 1%, and since we were able to cut down the volume, and because we only need the directionality of the sampling and or of the data, not the whole like data set for auditing, and so that's a good way to do it. Before you set up sampling though, make sure that you don't just like just set up whatever sample thing you want to do. This is something where like you do want to consult a data scientist about the data shape, so that like because it's very important to get a random sample. But for example, here is another thing to think about with like requests. I think this is a beautiful example where like I think as data engineers this isn't something that we think about that much. But like okay, there's two ways that you could sample the requests, right? Where it's like you could take a small percentage of all the requests and just do randomly take a percentage of all the requests, or you can take all the that we think about that much. But like okay, there's two ways that you could sample the requests, right? Where it's like you could take a small percentage of all the requests and just do randomly take a percentage of all the requests, right? Where it's like you could take a small percentage of all the requests and just do randomly take a percentage of all the requests. Or you can take all the requests for a small percentage of users. And like across the board. then like in this other case you get the full kind of makeup of like the whole like request flow for each user, and that's a better aggregation model than like in this other case where it's like you have like one request for this user, two requests for this user, and it's like kind of like you don't have their full history. So like the analytical capabilities of that way of sampling versus the other way of sampling is significantly different. So that's where like don't just like be like because it's easy to sample, very very easy to sample, like it's a one-liner to put that into sampling, but don't do that. Like, make sure to ask a data scientist. Like, that's my main point there. Unless you are amazing at statistics and you already have the data science skills, then maybe do it yourself. But I know I don't. That's one of the things that I recognize that I want to defer to a data scientist about, because that will make the whole process a lot better. So remember, sampling is another beautiful tool in your tool belt if your pipelines become more unreliable and you don't need the full data set. Okay, but like, when should you not sample? I think this is another important question. There's a good example here of like if you need the entire data set for auditing purposes or whatever, then sampling's not going to work, because you might be looking for a needle in a haystack, and if you sample, then the needle is gone, and you're not going to find all the needles that you are looking for. So audit purposes, nope, nope, nope. Okay, so that's sampling. Audits don't work. Go to the next one. Bucketing is very important. I'm going to give a couple examples of when I used bucketing in my career that were just mind-boggling how good they were, right? So big thing with bucketing, right, is so when you have a join, right? So if you imagine you have a join of two data sets, you have this big thing called shuffle, right? Where you can imagine you have like the left and right side of the joins, and then how it works is that join key gets hashed into a number, and then that number gets moduloed, like, which is like you divide and you take the remainder, and then that is the partition that row gets assigned to. And mostly this is done with like the default modulo in Spark is 200, because you want to have 200 partitions, and then that's how it works. The problem with a lot of this stuff is that that whole process of slicing all the data up and moving it around and then moving it across and then matching it up is very, very expensive. That shuffle operation is very expensive. So what you can do instead is when you write the data sets, the left and right side, say they both have user ID, they're joining on user ID, then you can write the left and right side datasets to their own partitions, essentially. So instead of writing like one big Parquet file, you write like maybe 1,024 smaller Parquet files that do that modulo operation already, so that you have them in 1,024 files. And then the right side is also in 1,024 files. So when you do the join, you just match up the files, right? And then the files just match up. And then you don't have to do all this crazy. There's no shuffle. Shuffle doesn't exist if you bucket. So, and that is, I highly recommend listening to the speaker series with Sundar. He's a senior staff data engineer at Apple, and he talks a lot more in detail about how he uses bucketing to solve hyperscale problems. So, and that is, I highly recommend listening to the speaker series with Sundar. He's a senior staff data engineer at Apple. Apple, and he talks a lot more in detail about how he uses bucketing to solve hyperscale problems at Apple at the petabyte scale. So bucketing is one of the most important optimization techniques, especially for the highest volumes of data, because once you have massive volumes of data, that join where it does that shuffle technique, that shuffle is broken. Like once you're over like 10 terabytes, shuffle just breaks down and becomes very expensive. So that's where you can get a massive performance gain if you just write both of the left and right side of the join to bucketed tables, because then you can do the join without shuffle and it's very performant. And so when I was at Facebook, this is a big thing I was doing in notifications, was I had the same problem. Where like the notifications table, I had like this. So one of the tables was called notif data features, which was like it was like a machine learning table that had for every notification it had the like a vector of features of all the different features of that notification, like when it should be sent, what content type it was, the probability that someone was going to click on it, the probability that someone was going to ignore it, like all sorts of different like a big vector of like hundreds of things, right? And then on the other side you have the actual events. You have the, oh, they clicked on it, they sent it, right? Because you need to merge these two data sets, because then you have the features and the facts. And if you merge them together, then you can actually train the model again, because then you're like, oh, we predicted that there was a 90% chance that they click on it, and then they didn't. So that's going to maybe drop the next time they generate a notification that's like that notification. It's going to drop it a little bit because that's going to retrain it. But anyways, that join was actually at the notification level, right? Because you're joining the notification features and the notification facts. And you join them together, and that join was very large. And so what I did in that case was you join on notification and on user. And if you do that, then and it was bucketed on user. So then you just line up all the files that are based on the user ID and bucket it. And then you can join those together. And then that removes all the shuffling that was in there before. And then that made that job go from taking, so before that job was taking up 25% of all of notifications compute. And then after I made that optimization, it took up 4%. So we got a massive increase in efficiency and also a ton of compute back. And it made it so our namespace was actually like working again. It wasn't just like on fire all the time. And so that was a big win that we were able to do with bucketing. So I highly recommend just checking out bucketing as well. Like we're going to do a little bit of bucketing next week in the Spark week, if yeah, because you're all in the infrastructure, so y'all definitely be in the Spark week. So it's good stuff. Like I definitely have used it a lot. I've used it at Netflix as well, and some other very hyperscale use cases. So that's kind of like another big thing that I would recommend looking into. There are drawbacks though. I think that I want to talk a little bit about how like it's not like because just because it solves these hyperscale problems, like I'm not advocating that every table be bucketed. And one of the main reasons for that is that say you bucket everything to 1,024 files, and it's like a small table. Then when you read it, it has to read in 1,024 files, and just like opening and reading that many files is slow. And like it's worth it when there's a lot of data, but like if it's not very much data, then the cost of like opening and reading all of those files is higher and more of a pain in the ass than if you just don't bucket. So that's why like this is something that is kind of more reserved like for tables that are at least over a terabyte. Like I would not recommend bucketing on anything under a terabyte. So that's because if it's under a terabyte, you might as well just shuffle, and you're gonna get like probably a better performance characteristics. So that's bucketing. Bucketing can save your life. Okay, so another big thing that can happen, another big signal for tech debt, right, is large cloud bills. So one of the things to remember about the cloud is there's essentially three places that you pay. You pay in I/O, you pay in compute, and you pay in storage. Those are the three places that you pay. With I/O usually being the biggest one. And because the main reason why I/O is the biggest one is compute is generally fixed, right? Because you like rent your computers on like a fixed basis. And then like you either have enough or you don't have enough. And then if you don't have enough, you need to buy more computers, and great. But like if you don't have enough, or if you have enough, then like you're going to pay the same amount anyways. And then storage is just generally really cheap, like especially in comparison to I/O and compute. And one of the ways you can think about that is, okay, moving data around and moving it from point A to point B is going to be one of the most expensive operations that you're going to have in your cloud bill. This is where like this is probably the one argument that I have for the signal table pattern. If y'all remember from week 3, we talked about the difference between write, audit, publish, and the signal table pattern. And this is going to be and this is Facebook's rationale as well of why they use signal table over the write, audit, publish, is because write, audit, publish actually does a partition exchange. So that means that every time that you write a table with write, audit, publish, you actually essentially do 2 times. You do I/O twice, right? You do I/O into staging and then I/O from staging to prod, right? And so that's where you pay your I/O cost twice, which is pricey. It's not cheap. Like it's actually it's like the most expensive part of your cloud bill. So that's why it's not as cut and dry of like you should use Write Audit Publish or you should use Signal Table, because of the fact that IO is just so expensive, so expensive. And that was one of the things that I noticed, like because when I was working at Airbnb, and I found some massive wins in storage and compute for Airbnb when I was like computing the savings that I saved for them. It was like essentially it was like, okay, I was able to save like 5% of all the savings was in storage, and then 10% was in compute, and then 85% was in IO. And obviously, this depends on the pipeline as well, because in that case, the reason why that was the case for me is because the pipeline I was working on had a lot of downstream usage. So if I was able to make the storage footprint of a table that has a lot of other pipelines reading it, then that's actually where you get the big win, the big savings, is where they read in that smaller table every day, and as opposed to reading in a bigger table every day. And then the savings you get is multiplied by the number of downstream pipelines. And that's why you get a massive IO win, because you scale based on the number of other pipelines that are reading from your data tables. And so that's where that's why IO can be so massive as like a win. But obviously, like if you're in the case where you're at the bottom of the like data engineering tree, where like your pipeline is producing a data set that is like visualized in a dashboard, and it's not master data, but it's like more of that final like metric aggregation layer, then IO is not going to be your biggest cost. It's going to be compute probably. It's going to be close between compute and storage. Probably compute, and then storage would be your highest cost, because you don't have that multiplicative effect of all those other pipelines reading from your pipeline. So cloud bills, there's a lot more we're going to talk about here with cloud bills, because I think this is a big area where you can have a big win, both in terms of efficiency and in terms of maintenance. Okay, so let's talk about why too much IO can happen. Okay, so obviously the first one is duplicative data models, where you have like when I was at Airbnb, there was when I first started there was 7 different definitions for availability. Like is available, there was 7 different ways that people define that, and it's like why, like why are we doing that? Like, and I mean, it's like that pain is actually that pain is not just an IO cost, right? That pain is also in communication overhead, where it's like I say available, you say available, but we mean 2 different things. And so like you also like in some ways that's even the bigger cost is on the communication overhead, because employee time is just so expensive. So like that's but like IO cost as well, because it's like why do we have 5 different tables for this when we should have one? And then those pipelines write every day, and they are generating these tables every day. And so duplicative data models, not enough robust data modeling, big place where you eat in IO. You have inefficient pipelines. So imagine if you're doing like the monthly active user pipeline, and what you do is you just read in the last 30 days of fact data, and you do it that way, and you make Zach sad because like I taught you better than that, and like I taught you to use cumulative table design, and because you don't need to scan 30 days of data to process this every day, you can scan 1 day of data and then the historical and then 1 day of data to calculate monthly active users. And so that's another place, because in those cases, if you're scanning 30 days of data every day, that's a lot of IO, right? You're reading in 30 partitions every day when you could be reading in 1. another big place where you can eat a ton of IO cost, and I'm always like so painful, so painful. It'd be another place because in those cases, if you're scanning 30 days of data every day, that's a lot of IO, right? You're reading in 30 partitions every day when you could be reading in one. Another big place where you can eat a ton of IO cost, and I'm always like so painful, so painful. Ow. You also have excessive backfills where maybe you are trying to backfill a data set and like you're kind of hasty about it, and you didn't validate all of your pipeline code yet, and you didn't like really thoroughly validate it. This is where Airbnb's Midas program, like they try to avoid these IO costs by they say first backfill 1 month of data and then validate that, and then if that looks good, that 1 month of data looks good, then backfill the whole history of the data set, because then you don't pay these IO costs over and over and over again if there's a bug, because that's happened to me before. I've been there. I've made this mistake myself many times, like probably at least 3 or 4 times in my career, where like I've backfilled 7 years of data, and then the analyst comes back to me and is like, these numbers don't add up, and then I'm like, wow. Like I just gave Jeff Bezos like $5,000. I'm sorry, Jeff, or like you're welcome, Jeff, and I'm sorry, Brian Chesky or Reed Hastings or Mark Zuckerberg. I guess Mark Zuckerberg he owns his own infra, so like it's different there. But at Netflix and Airbnb, they both like give Jeff Bezos money. So, anyways, backfills. It's another way that you want to be careful. Make sure to follow backfill best practices and to be very confident that the data that you're going to backfill is going to be correct, so that you don't just do it all over again, because backfills are very expensive, because it's like running all of production for 7 years. Like that's like a lot if you're depending on how much history you're trying to backfill. Then you have not sampling. That's the case where like you feel like you have to use the entire data set when you don't actually have to use all the entire data set. You can do it without all of it. That's another kind of common problem I've seen. Uh, Also, not subpartitioning correctly. So subpartitions can be great because, especially if your data table has another low cardinality column where you get that, like you can split the data up in a more a cleaner way. We're going to talk about that. I have another slide here because predicate pushdown can be amazing in that case. Because if you have a subpartition, what it allows you to do is it allows you to avoid reading in a big chunk of data that you don't need to read in. And because it just ignores that folder, because it gives you another layer of folders, and it says, oh, our query doesn't want that folder because it's filtering it out, and we don't even have to read in the data. We can just ignore it. And so that's where subpartitioning can be very, very powerful in avoiding large cloud bills. There is some trade-offs there, and like I think that there are definitely cases where I've seen subpartitions used incorrectly as well. But that's generally speaking, this is how I would imagine things would work with large cloud bills. Those are going to be your big ways that big symptoms or big causes of large cloud bills that you can probably fix. Let's talk a little bit about why subpartitions work. So imagine you have a table here. We're calling this table notifications, and then